So as you see, mostly my background is really on classical networks, so optical and wireless classical networks. But back, maybe a few years back, we started what's called a US-Ireland joint project. That's why you see an A here. So we started working with a group from Bush here, and we're still looking at problems of mixing up the classical networking with the quantum networking. So it's really about how do we, what if you want to be practical, like how do we actually transmit entangled photons over an optical network? This is something that we all know. Once we have quantum computer, like with classical computer, the next step is going to be how do you interconnect them for multiple reasons. Whether you need, for maybe even less reason, because in a classical network, you need to connect to a computer for control plane and data plane. In a quantum computer, probably your control plane is still classical, but you might need quantum network for your quantum data plane, and you need why you do a quantum data plane is for application like UKD, sensing, or distributed quantum computing. Of course, you cannot transmit the state directly because once you lose them, they're lost. So your real data plane communication quantum network, it's an entanglement distribution network. Now, how do you build this entanglement distribution network in reality? Okay. Again, we have divided this into the physical quantum network, which is the data plane where you transmit your qubits. Then you got an virtual entanglement network, which is after you have your qubits, you have entanglement, so you have entangled links between the nodes. And then you have another physical network for your control plane. Now, the data plane, how do you do it? There's a number of options. Okay. Now, I put them in order of infeasibility, or not infeasibility, of economical infeasibility, if you want. So the best thing you could do is build a completely new fiber network based on hollow core fiber. Okay. If money was an issue, if you could actually produce so much hollow core fiber, that's probably what you would do in the first place. However, that's could be far away. Other thing you could do is that you build a dedicated core, you use the dedicated core over a multi-core network. Again, you have to deploy multi-core fiber. Although now that this seems a reality, this probably may not be a good option anymore. Why would you develop multi-core fiber when you know that hollow core fiber is coming? More realistic, as of if you want that today, you would use probably a dedicated fiber over a shared optical cable. So the optical cable is already there for telecoms. There is a spare fiber, you use that one. Or another thing you could do, this in principle could be cheaper, but it's not really clear because probably the components are going to make it more expensive, is just share a WDM network. Okay, there is channels on one fiber. You either use a band that's not being used. For example, you use the O band when the telecom sits on the C band, or else there has been experiments where you actually you share the C band even with some of this. Anyway, so these are options that you can use. Now, with respect to the virtual entanglement network, we don't really address this much because, I think this is all about, this represent the received entangled states. Okay, so this is more about the algorithms that you might use on them. But the things that we focus as well is on the control plane network. How do you implement the control plane network? Now, again, how would you do it? Now, if money wasn't an issue, you could create it. No, why not? You could have your hollow core fiber also for the control plane. For no other reason that you're a third faster than a normal fiber because you're on vacuum. Which, going ahead, this might be an advantage. Second thing, you use a dedicated fiber network. And the reason you might use a dedicated fiber network, again, is because you could get a more direct route between the nodes in the exchange information. And that's, again, is lower latency. And I'm going to explain why latency is an issue. Or else, you can use a spare fiber over the quantum network that you used above. Or else, cheapest option, why don't you use the IP network? Right? The IP network is there for transmitting packets. Your classical side of the quantum protocol is transmit packets, so why not use that? And we focus on, we do some analysis of what happens when you try to do that. Now we start first with this part, so the physical quantum network. And so this is again work we published maybe last year. So this is about how do I route entangled photons. Now we have a couple of assumptions. So you have, let's say that you have the source on one side, and I'll show you later. The source is a broadband source. And basically from that source, you want to distribute entangled photons across all the other nodes. Okay, so the source is on one side and you want to transmit the entangled photon there. Now, this could be a non-degenerate source where the photon, well, the two entangled photons are on two different frequencies, wavelengths, or else it could be degenerate. For example, this is the case of the Zaun source, which is also heralded. Now, in terms of routing and computing, really computing the routes, the main difference is that if it's non-degenerate, then you can use classical normal optical routing because these are different wavelengths. If it's degenerate, you cannot use the same route. Okay, the path has to be the route has to be path disjoint because these are the same wavelengths, so they cannot travel over the same fiber. Otherwise, you cannot distinguish them here anymore. Okay, now this is an example, okay, how do you actually practically do this? I mean, this is fiber, okay, that's fine. But what are those nodes made of? And again, here is the idea is that you use what's in there in the classical networks. And there are these devices called wavelength selector switches, which pretty much it's a device where you put one fiber in, multiple fiber out, and what gets out of each of the ports, it depends on the internal configuration. So these are a configurable wavelength add drop multiplexer if you want. So you got your broad source here that comes from here. Again, the same wavelength that goes on both sides. And here you decide which part of the spectrum you use to send into different direction. That's what you do. Of course, if you need to send larger number of pair, you just use a larger portion of this band. And basically what you have is that if you have 20 nodes, you have to decide how much band you send, and that determines how many photons per second you're going to send to each node. If you want to implement fairness, you make it in a way that you give a larger portion to the nodes that are farther away due to the loss, things like that. But that's the concept, and this is kind of the architecture. Now, of course, the problem is that, I mean, if you want to do this multiplexing, you have to go through these devices. They add the loss. Now, depending on which port you use, on a number of things, this normally goes between 4 to 8 dB, depending on the configuration. And I know they are lossy, but if you want to use a classical network, that's what you have to do. Otherwise, you will need to have an N by N direct point-to-point fibers, which, today is very hard to, it's not very economical. Okay, so we did, so this is a couple of paper one. The first one was ICC and the second one was JSAC. So this is just some experimental results. Say, take a network like Manhattan. This is actually a metro network, a realistic metro network simulated from Manhattan. And basically, you look at the results and they say, okay, assuming that my node loss is 4 dB, this is the minimum number of pair that I get across the network, depending on where I locate my source. Okay? So, for example, here we show that the source location has an important meaning. Okay, so you want to put your source where you minimize the overall distance across the network. And if your loss is higher, this becomes even more important, and it looks like some nodes have a more remarkable difference across that. So this is some initial work on saying, what does it mean to use an optical network to transmit entangled photons and what type of results you could do. The interesting thing is that you can actually do this today, right? You get an entangled source, you get this type of devices, which we have, and you start verifying in what you get on the other side. Okay. Now, the next part is that how should you implement your contour plane in a way that's, can be usable and realistic? Now, most applications apart from QKD maybe, most applications will require storing entangled pairs until they can be used. Now, because even if you go point to point, at least the fiber has got some loss. The nodes has got loss as well, but the fiber has got some loss. So if I transmit 100 photons in two directions, even if the loss is the same, let's say 3 dB source, 3 dB loss, 50 will get there on each side, but I'm not sure which 50 got there. And to have entanglement, I need to be sure that the same entangled photon gets both pair. So at least I need to run a protocol that try to understand, okay, I received this photon is entangled with the other photon, we keep them in the memory, and we know that these two are entangled. Okay, so this is called the matching problem. Now, Of course, what's the issue is that while you store, because you don't know which photons is which, you got to store them first in your memory, and then you start a protocol that start communicating with the other nodes to understand which one did you receive, okay, which one we agree that are usable. Now, this also assume another thing, which I'm not going to discuss too much here, but just to put it there, that there's also the problem: how do you label your photons when they come out of your entangled source? Okay, I mean, you need to label them because if I'm a node, all I receive is photons. So how do I know whether this is entangled to some other photons? How do I even tell the other person I received this photon? Can we check it? Okay, so of course, you need some kind of label. Now, how do you do the label? I mean, if you have a synchronous network, this is very, old style classical networking. If I have a synchronous network, a time slot is itself a label. This has been used for a very long time in classical networks like SONET or SDH. And typically, in a TDM system, the position of your time slot already tells a label for the slot. Or else it can be asynchronous, which means you need to send a packet. Now, this packet has to be associated with the photon that you're sending. And the question is, how do you do that? Of course, you want the photon, the entangled photon, and the packet to travel together, because when they're received, you need to know that this label belongs to this photon, and so on. So there are these type of problems. But for this work, let's assume that you're going to solve this problem, that you already have a label when your photon arrives. Okay, so then what you need to do again is communication, so that you can say and you can agree on which photons are entangled, so that your back here. So this layer here knows exactly which pairs are there and which pairs can be used. Okay, now, again, as I was saying, while you store even assuming that as soon as you identify an entangled pair between two nodes, you can use it straight away. Okay, so you're not queuing them. Once they're usable, they're used straight away. You still need to queue those entangled photons, at least until you have identified which photon is which. Now, the problem is that the quantum memory is going to have a decoherence time, okay? And the question is, the protocol is going to take time to transmit, so you're going to have latency, so you want low latency, but how low should your latency be, okay? Because, at least it's going to be as low as constrained by the speed of light, but again, if I want to use an IP network, it's not just the speed of light, there are other issues. And the question is, do I really need to use a dedicated fiber network, which is the lowest possible latency that I have, or can I get away using an IP network in a practical situation? So, how do you address this? Well, if your problem is latency of the network versus the coherence of quantum memory, you just pick both of them and you see, what's the mismatch between them. So, for example, these are statistics for the Greater Dublin area broadband network. So, what's the latency in milliseconds that you get across a network? This is the distribution. And then on the other side, you look at what are the memory technologies that might be around today, and you look at what are the T1 and T2 parameters. And then once you have this, you start doing some simulations, and you assume that you generate entanglement. Your sources at one point, and then you have to entangle B and D maybe, and C and E. And then you just look at, if this is my classical IP network, the distribution of latencies, what's my fidelity loss as the memory decoheres over time. And again, you can see that depending, of course, of the type of memory that you use, you're going to see where you are. Now, this also tells you, depending on the memory that you use, whether do you need a dedicated fiber network or not. Because if you are in this type of memory, then a fiber network, maybe it's around here of latency, versus an IP network doesn't give you much advantage. Okay? Of course, if your memory is somewhere here, or even something like that, then there could be a big difference. Okay, it really depends what memory is going to be feasible to use in these situations. Okay. Now, and again, so this is the same. This is just the same work. So this was proposed. We presented this at ICC this year. And then these are just some more results from the same work. What's the buffer that you would need in terms of quantum, no, ideally, this is in simulation, in terms of quantum memory. And again, the other issue with the latency is that the higher the latency, the larger the buffer you need, because again, you need to store until your your matching pair protocol has converged. And similar here, again, they give you some threshold. If you want a certain threshold, because again of the memory decoherence, then you're constrained by a certain maximum latency in milliseconds. So the question whether, how low is your latency and whether can you use an IP network which has additional latency and jitter, or do you need a dedicated network? It really depends on a lot of these factors. What's my target fidelity and what type of memory is it feasible to use for the system that I'm thinking about? Okay. So now what happened again? Imagine you've done your calculation, but what if by this calculation, the fidelity that you get is not enough? Okay. Well, what can you do again? One thing is that, okay, I'm not going to use an IP network. I'm just going to do everything on hollow core fiber. Okay, less loss on the data plane, faster, lower latency on the control plane. So you can do that. Or else you say, okay, I'm going to instead do something else. I'm going to sacrifice the number of pairs that I get, but maybe I run an entanglement purification algorithm so that I can improve my fidelity. Now, the interesting thing, of course, is that it's always that of latency, right? Because an entanglement purification algorithm needs classical communication, which has got latency. So the problem is that, if your latency is bad enough, by purifying, you're actually losing, okay? Because I mean, you can see here, depending on the latency of the networks, this is, so basically is the concept of running a purification algorithm at the endpoints using classical communication, depending on the latency of your system. This shows for two entanglement purification protocols. So the first one, BBPSSW, the second one, DEJMP. So, I mean, it shows that, okay, this one, of course, from what you see, performs better. But again, as you expect, if your latency is too high, your purification is going to just make it worse because, remember that the memory keeps decohering while you're running your purification protocol. So there are thresholds, again, depending on the network size and so on, after, below which there's nothing you can do. But otherwise, you can, depending on the algorithm, again, that you use, you can improve to purification. Of course, you're going to sacrifice a number of pairs for that. So again, what do? Do you build a hollow core network, or else do you try and inject more photons? Maybe you have multiple sources to have more pairs. Okay, that's the ideas. And yeah, this just shows more results. So this shows the fidelity versus network latency compared to how many EPR pairs you need to consume if you want to achieve a certain fidelity. And this is the distillable rate with respect to the network latency. Okay, and so as I said, it's going to be brief. So, I mean, the way you see this is that it took a long time for the internet to see what it is today, right? It took over 50 years to build it to the places now. And I mean, I'm not sure how long it's going to take to build quantum computers, but how long it's going to take to build the quantum network. Now, if you don't want to take 50 years, you really have to reuse what's there at the moment. Okay, there's billions of kilometers of fiber in there. A lot of them are lowly utilized. So I think it's important that you look at that. And I mean, of course, the economic drive for the quantum networking, at least at the beginning, is not going to be as strong as the one that has been there for the internet, right? I mean, the internet has a lot of economic value behind. I mean, quantum has got a lot of investment now for, there's a bit of a quantum hype. But of course, in terms of revenue generation, is nowhere near where the internet has gone. So the amount of actual investment that you could have to build that network is still probably quite low. So to me, the quantum internet is going to be a lot about an engineering problem. Okay. And by this, I mean, really, it's going to be about the trade-offs. Okay. Trade-offs, you don't just go for the solution it's the best solution, but it's got the solution that is the most viable with what you have at the moment. And I think a lot of the work that we're doing is around this for this reason. And yeah, that's all. I'm going to conclude here. Just some acknowledgements. Again, I'm going to name the people because they've done a lot of work here. So we have Vivek, Vasan, Rohan, Anuj, Ashley, Jerry, Shelby, Alexander, Dan Gilper, and Bulat Bashir. And you can see who is from Trinity College and who is from University of Arizona.
Yes, thank you for the nice presentation. Are there questions or comments? Oh, I see.
Thank you very much for the talk. I have a question for your two purification protocols that you're running or evaluated. Do they need classical communication to how do they work?
Yeah, I'm not going to do the detail, but basically, you do a quantum operation and, as usual, you get the results of the quantum operation and you communicate it to the other node.
So you need classical communication
Yes,
too.
yeah,
Okay.
yeah.
Because this is also what I'm currently working on a little bit, just from a information theory side of things. What I realized is if you can do it, project one of your qubits on one side into a GHZ state.
Okay.
And then you can run local purification with another sacrificial pair, but you don't have to have classical communication to the other side, and you have some fidelity improvement as well.
Then do you know how those compare to the classical?
It's worse, but you, in terms of fidelity gain, but you have no communication, which is, I think, the bottleneck. In the end.
I mean, yeah, okay. I mean, you probably give you an advantage on this part here. Because, I mean, you're going to sacrifice more pairs, right?
Yeah. I think like there will be a threshold at which you need to,
I mean, for sure, this one that really suffer from the latency, then, could be, that could be something,
There was another question.
So I think there's a reply,
Sorry? Yeah. Yeah, thanks a lot for the talk. Could you go back to your slide, maybe number 3, where you have the 3 like parallel abstract internet structure? Yes. So you say that we'll need a classical network to run these protocols and support the quantum operations. So do you think it makes sense to believe that actually the support network will be in itself also working quantumly? And that will allow to more efficiently support these operations?
Yeah, what's the advantage, what's the advantage of the quantum network to transport classical information, right? I mean, unless...
So it could be that to support these operations, we need to solve some distributed tasks, and then we have quantum algorithm which goes faster than classical ones.
Possibly, yeah. I mean, at the moment we're really using very simple. I mean, the algorithm here is about I have pair number 3, I have pair number 4. No, they're not much. I have 5. Oh, I have 5. So let's use this. So at the moment it's very simple. But yeah, in principle, yeah. I mean, especially if it's more about, on the sensing side, maybe when you're actually supporting some complex, or even on distributed computing, something complex on the data plane, absolutely, yeah. But
yeah, so first of all, we just heard from Holger Bosch about the fact that the algorithms that will help us here probably don't exist, in fact. That's how I interpret the talk, maybe. So I don't think there's any hope in the near future that you're going to get some kind of advantage algorithmically. Point 2, we heard from Saikat. I don't know whether he is here or not. It looks like he left.
It was earlier on.
But we heard from Saikat yesterday about the futility of using entanglement resources for for enhancing communication. So I think that one of the reasons why I am involved in this is because from engineering standpoint, this makes the most sense. You have a precious resource, entanglement, that you can use for many things that are very relevant, like sensing, for instance, and you need a way to distribute it. Now, to the point of Benedict, right? Who's asked the first question? I forget who that person over there. I think that if you could share that protocol that you mentioned that doesn't use communication in the distillation stage, it would be interesting because there might be a threshold where it might work. You still have, at least in this scheme, you still need classical communication, because if you're storing the PR states in quantum memories, you need to be sure classically, if you have heard of them, either at the memory or at the source or both, that you have the right state. So there is some classical communication that again will be needed, necessary. And I think that if you don't have classical communication, there might be some non-locality stuff that physicists don't like to break, also kind of come into effect, but I'm not sure. But anyway, yeah.
But I mean, you need classical communication, but I think the point was if you're doing purification, you can do purification without.
Right. So
And I think it's really about, I would take it engineeristically, it's really a trade-off. If it's more effective to put a higher number of entangled sources across the network, so you generate more pairs, so you can consume more, that's give you a better solution, that give you a better solution. There's nothing to compute it.
Right. So this is why it's important to look at what you're studying as well. It's very, there might be a trade-off that we could exploit to engineer the system better.
Yeah, of course, it's a trade-off. But I think what is kind of the main bottleneck is to actually get entanglement in your memories, and then you want to keep it as long as possible. So, kind of using then sacrificial pairs might be not like the communication-based purification might not as be beneficial, because in order to get then to a higher number of entangled pairs, you would need more time, and this can be a problem. But of course, it's kind of, we have to see that.
It's all numbers. We put numbers together, and whether is the latency more of a problem than the number of pairs that you have? Because at the end, you need to satisfy the demand of pairs as well, right? Because that's what's needed.
Yeah.
I think it's you crunch in the numbers, that what gives you the higher number of pairs of that fidelity, and that's your answer, yeah.
Okay, then thank you.